But there is another neat method to do this problem, a very nice cute method which is based on calculus. So let's solve the problem using that method. So I will redraw the figure for the purpose of clarity. So here the particles were initially at the corners of this equilateral triangle, the side of which is A, and particles are moving with a speed v, always aiming towards the next particle. Now we will take the situation at some other instant, at some intermediate position, which is after certain time t. After time t, if we observe, the particles may be here. So they are actually going in a very complicated path. So the particles may be here. So at that moment, I take the separation as S, the separation between these particles as S. Always they will be forming an equilateral triangle. Now let's see this using a magnifying glass. This separation which I am showing here, I will magnify it for the purpose of illustration. So I am drawing this triangle as a bigger one to magnify the view. The separation is S. Now this is at some time t. After further dt seconds, here dt is an infinitesimal. Its value is 0. So after a very small time, I shouldn't use the word small actually, it's an infinitesimal. After an infinitesimal time, these particles would have changed their position. So each particle would have moved a distance of v dt because they are going with a speed v. So the first particle would have gone a distance of v dt, the second particle would have gone a distance of v dt, and so is the third particle. It has traveled a distance of v dt. So the new position, if I separate them, if I join them, the new position is like this. Now I take the separation as S plus ds. So I am assuming after time t plus dt, separation is S plus ds. Remember, ds is a negative quantity here. The separation has reduced in fact. So actually ds value is negative. We must remember that. But with increasing time, I am assuming the separation is increasing, where actually this ds is negative. Now the new separation, S plus ds, can also be calculated in a different way. See, this is nothing but hypotenuse of this right triangle. I am drawing again and again the same right triangle. So S plus ds is hypotenuse of that right triangle. So I can calculate the hypotenuse as square root of base square plus altitude square. But I must get these. This angle is 60 degrees. So this will be v dt cos 60, v dt by 2, component of displacement in the horizontal direction. This is anyway v dt. So this total is S. So this will be S minus v dt by 2. Do you get that? Total separation between the particles initially was S. So that S minus v dt by 2 gives you this. So it will be S minus 3v dt by 2. That will be this separation. And what about this? This will be v dt sine 60. So I can write that as v dt root 3 by 2. So I got both of them, so-called base and altitude of a right triangle. So I can get the new separation S plus ds as square root of base square, which is S minus 3v dt by 2 whole square plus v dt root 3 by 2 whole square. So if I simplify this, it would take up the form S square minus 3sv dt plus 9 by 4 v square dt square plus 3 by 4 v square dt square. See, here we are dealing with first order calculus. dt itself is an infinitesimal. dt square, you can neglect it without affecting the precision with which we are solving this problem. So dt square can be neglected comfortably. So I can write this as S, if I take common, into 1 minus 3v dt by s. Do you see that? After neglecting this, I have taken s square common. When it comes out of the square root, it becomes s. The remaining terms are 1 minus 3v dt by s. Now here, this is a very small term because of dt. So I can use binomial approximation. So in fact, you have 1 minus x whole power n is approximately 1 minus nx. Using your binomial theorem, when x is very small compared to 1. Because this is very small compared to 1, I can write it as s into 1 minus 3v dt by 2s. Can you see that? This is 1 minus 3v dt by s whole power half. The half has come and multiplied this. Whatever is n, it comes and multiplies it. So I can write it as s minus 3v dt by 2. I have taken s inside. So s plus ds, we are getting it as s minus 3v dt by 2. From there, I can cancel s on both sides. So ds is minus 3v dt by 2. Let's integrate this. Initially, at t equal to 0, when I started observing these particles, the separation between them was s. So at t equal to 0, the limit here is s. Finally, after some time, t, they have met. The separation between them is 0. So we must have 0 minus s, which is minus s. On integrating this, I get s. When I put limits, I get 0 minus s. And here, I get minus 3v by 2 into t. Remember, v is speed, which is constant. So I have initial separation is a. So I have t is 2a by 3v. So I'll make this correction. The initial separation between the particles is a. So we get 2a by 3v. So it's a very neat method using calculus. Okay. So I hope you got the concept here, what we are trying to do. Sometimes there can be another question based on this. Suppose they'll ask you to find the path length. Then you have to do that in the same manner. The path length followed by the particle. Okay. So based on this, I'll take one more question which will help you understand this better. So the next couple of problems which I am going to do are really involved, and hopefully they'll help you understand this topic better. So the first problem is, I have a river whose width is d and the river's velocity is u. There is a person whose velocity in still water is also u. Yesterday we saw that this is nothing but velocity with respect to river. We also saw that you can say this as velocity with respect to river. So person's velocity is also u. Now there is a point A here on this side of the bank. There is a point B on the opposite side, and it's a river which is flowing with u. This person, of course, cannot reach directly point B, because even if he tries to counter the river fully, he will be at A only. Suppose he is swimming in this direction with u, river is also going in that direction with u, he will stay there. Net velocity is 0. He is trying to go, river is pushing him, so he will stay there. So if his full velocity is unable to compensate the river's speed, then not to speak of the partial velocity, the component. So in fact, even if he tries to swim that way, only part of his velocity counters river. So he cannot compensate the river speed. So he is about to drift. He can never reach this point B. But he swims in a strange fashion. What he does is, he is always swimming by aiming towards B. So right now he is aiming and swimming in that direction with speed u. After some time, the river would have taken him to the right because the river is flowing. So he will be here. He would have gone ahead, river also took him to the right. But now he is aiming towards B and again swimming like that. After some more time, the river would have taken him to the right and he would have gone a bit further. Again he is aiming towards B and swimming. So in this way, he finally reaches there and now he is aiming towards B. Of course, he is aiming and trying to swim with the speed u. River is going with the speed u. So both cancel, he will stay there itself. So he is always aiming towards B and then swimming. The width of the river is d. And all we have to find is this distance BC. So what is this distance? This is what we have to find. Where does he reach on the opposite shore? How far does he reach from point B? He was supposed to reach point B, but he can never reach point B because his speed is same as river speed. Had it been more, there was a possibility to reach B, because he would have he would swim in this direction, and then automatically part of his velocity cancels reverse velocity, and remaining part enables him to go there. Had his spin been greater than river speed, but his speed is equal to river speed, so he won't reach that point. He will reach there, and he is always aiming towards B. He's always aiming towards B. Now we have to find this distance BC, which is called drift. Where does he reach from point B? It's a very tough question to solve it using normal principles. So what I do, at certain intermediate position, somewhere in between, I see that he is trying to go in that direction. Let us say I will take two perpendicular directions. Let us say this angle is theta. The angle made by his velocity vector with vertical is theta. Okay? And of course, river is also flowing in the horizontal direction with a speed u. Now, his vertical component of velocity, his velocity in vertical direction, person's velocity, is u cos theta. So his velocity in vertical direction is u cos theta. What about reverse velocity in vertical direction? It doesn't flow vertically, it flows horizontally. So it doesn't affect his vertical velocity. And his horizontal velocity is u minus u sine theta. Can you see that? U cos theta is his vertical velocity. U sine theta is his velocity to the left. But river is also flowing to the right. So u sine theta. If you take the net, it will be u minus u sine theta to the right. This is at any intermediate position. For example, initially this angle theta would have been 0. Why? Because he is directly aiming towards B. Finally, this angle theta is 90 with the vertical. At any intermediate position, the angle made by velocity vector with vertical is theta. So we have these three things. Now let's apply kinematics in the vertical direction. After all, when he reached here, this is his total displacement. The line joining A and C is his total displacement. If you take component of displacement, AB is vertical displacement. So I can write integral u cos theta into dt if he takes t0 seconds to reach opposite bank as d. Let me explain this a bit. His velocity with which he is going up is not constant. This theta is changing. So his velocity is changing. Initially it was u, vertical velocity. Finally, he is in the horizontal direction. His vertical is 0. When theta is 90, his velocity is 0. So this is a variable velocity. So when he is going with a variable velocity, I will take a small time for which you can approximate the velocity as a constant. So this small time into this velocity gives you little displacement in the vertical direction. By integrating, I am adding all these little displacements to get total displacement. After all, he traveled for a time t0, let us say. So this is one equation. So this equation is for the vertical direction. Vertical velocity into small time gives you vertical displacement. By integrating add all these vertical displacements to get total displacement d vertically. Similarly, we have horizontally integral 0 to t0 u minus u sine theta dt. Horizontal velocity multiplied by small time gives you horizontal displacement. By integrating, you are adding all these little horizontal displacements. You get the total horizontal displacement, which is our x. This is my second equation. Of course, with these two equations, we cannot do anything. This is where the crux of the problem lies. Here you have cos theta. Theta is a variable. I cannot even take it out of the integral. Theta keeps changing as the person keeps going. Similarly, there is sine theta here. It's a variable. So I cannot do anything with these equations as of now. I cannot take theta out. I cannot eliminate theta. What is my aim? To find x. Then how do I find x? What is the point here? There is one more equation. You see, the person is always aiming towards B. So you can connect the person and the point B with a rod. The person is going towards the rod. Rod is also turning and shrinking simultaneously. What is the person doing? Person is going on the rod. But what is happening to the rod? The rod is turning and also shrinking. So let's see how he is approaching this point B at some intermediate position. At this position, what is his approach towards B? Approach means velocity along the line joining them. Velocity along the line joining them. So that velocity is given by u this way, and this angle is theta. This would be 90 minus theta. So reverse speed along that line is u cos 90 minus theta or u sin theta. Do you see that? Reverse speed in that direction is u sin theta. Person's speed is u. So how fast he is approaching the point B? U sin theta. So it will be u minus u sin theta is his approach. Approach means along the line joining them. That means along the rod. Along the rod, the person is going with that speed. So if you multiply this with small time dt, I should say infinitesimal time, as I said previously, this will give you a very small infinitesimal displacement. If I integrate all these displacements, I must get the total displacement covered, or the total distance, or total displacement killed rather. See, he's on the rod. He's going on the rod like this. Ultimately, the rod length is also decreasing. As he's going, the rod is following behind him. So finally he comes here and he stays there. So originally length of the rod was d. Finally length of the rod is x, because the rod is going like that. So how much did he cover? From d, the separation became x. So he covered d minus x. D minus x has been killed by him or destroyed. Approach equation. This is a very powerful equation. This is my third equation. Can you see that 2 and 3 are absolutely the same as regards to the left hand side? U minus u sin theta dt, u minus u sin theta dt. They are absolutely the same. So right sides must be same. So we must have x equal to d minus x. And without even solving these integrals, I am able to get the solution. Do you see from here? 2x is d, x is d by 2. It's a spectacular way. So in such problems, you don't solve integrals, you eliminate integrals. You eliminate integrals. So I'll take up one last problem based on this model, with which we'll conclude this session. This last problem also follows the similar theme. So the problem is, there is a rat which is going with a fixed speed u along that line. We keep seeing such things in our house. And there is a cat here which is following the rat with a speed v. Initial separation between them is L0. So the cat is always following the rat. The rat doesn't know that this cat is following it. So the rat is going on a straight line with a fixed speed. This cat is always approaching the rat with some speed. Its actual speed is v. We should calculate the approach speed. So after some time, the cat catches the rat there. We have to find the time after which it catches the rat. It's a very involved problem. So let's see that. Let's say in t0 seconds, cat catches the rat. Again, we take some intermediate position, somewhere in between. Whenever you have a curve, tangent gives you velocity, the direction in which you are moving. Tangent gives you the velocity direction. So the cat's velocity is in this direction, v, and here v is greater than u. I must enforce that condition. And the rat should have been there. Why there? Because cat is always approaching the rat. At this moment, let us say this angle with horizontal is theta. So horizontally, whatever is the rat's displacement, same is the cat's displacement. See, cat's net displacement. Displacement is a line segment joining initial and final points. So net displacement is this. If you take horizontal component of this displacement, it is this. So as far as horizontal displacement is concerned, rat speed and cat speed are same. So we must have u t0, the time after which the rat is caught, should be equal to v cos theta dt integral 0 to t0. This is my first equation in the horizontal direction. In the vertical direction, let's see in the vertical direction, cat speed is v sin theta. So we must have v sin theta dt. Why am I not directly multiplying by time t? Because theta is not a constant. So v sin theta is a variable velocity. So I am taking a small time, finding displacement there and integrating. Okay. This velocity is variable. So in a small time, find displacement, integrate. Integration means to add. Integration is a special kind of addition. So from 0 to t0, this should give us vertical displacement. Vertically, how much did the cat cover? L0. So it should be L0. See, this is the total displacement of the cat. I can split it into two parts. Vertical displacement, horizontal. Horizontal is given by ut0 because the rat covered ut0 in t0 seconds. Same with the cat. Vertically, cat killed this L0. So this is vertical displacement. Then we must have the approach equation. See this carefully. This is the most tricky equation. This is u. So along the line joining them, this angle is also theta. Why is that? These are two parallel lines intersected by a transversal. So these two angles are theta. So along the line joining cat and rat, the approach speed is given by v, cat speed, and u cos theta, rat speed, dt, integral 0 to t0. What is this telling you? Join both cat and rat with a rod. The cat is moving with this approach speed on the rod. Rod may be turning, but what is cat doing? It is moving on this rod. Okay? So this is approach speed. And what is the distance that the cat traveled on the rod? L0, because after all, you can move the rod and cat is moving on the rod. Okay? So we must have this equal to L0. This is my third thing. Now, this equation is useless as far as solving this problem is concerned. All I have to do is eliminate cos theta integral. So from this first equation, I can get integral 0 to t0 cos theta dt as u t0 by v. How did I get that? I took v constant, divided u t0 with v, and I got this integral. We'll substitute this into the second integral. This we will use and put it in this integral. So I'll split this integral into two parts. First part is integral 0 to t0 v dt, integral 0 to t0 v dt, but v is a constant, so I have this. V, speed of the cat, is a constant, minus you have u integral 0 to t0 u cos theta dt. Can you see that? I'm splitting this integral into two integrals in which v and u are constants, so I'm taking them out of the integral and I'm left with cos theta dt. I can put that cos theta from that. This is given as L0. So what do I get if I solve this? So let me make some space. So I have v t0 minus u into this integral I got from here, u t0 by v is equal to L0. So we have t0 as L0 v by v square minus u square, which is the time after which the cat will catch the rat. So hopefully you got something to learn from this topic, which is very interesting. So I would again remind you that if you have any doubts, you can please call the number that is being displayed below your screen. Thank you.